For Lewis dot diagrams, they can also be called electron dot diagrams. They mean the same thing, or they're referring to the same thing. So in Lewis dot diagrams or electron dot diagrams, we're using electrons, or we're using dots to represent electrons. Okay. However, we're not going to be drawing all of the electrons that belong to a certain atom. We're only going to be representing the valence electrons because those are the electrons that contribute to shape and bonds. And by shape, I mean the shape of the molecule or compound. So for valence orbitals, according to the theory of quantum mechanics, valence electrons are found in the outermost energy levels, which are called energy shells. Okay. And we have to be aware of the following rules. So there are 4 valence orbitals. So keep in mind, now that we're talking about quantum mechanics here, we're going to shift from calling the shells that electrons are in. We're going to shift from calling them orbits, which is the terminology we used when we were drawing our Bohr diagrams, and now we're going to be calling them orbitals, which specifically references quantum mechanics. So there are 4 valence orbitals in all atoms except for hydrogen and boron. Hydrogen atoms are only going to have one orbital, and boron is going to have 3 orbitals. So an orbital may contain either no electrons, 1 electron, or 2 electrons. Electrons are going to occupy any empty valence orbitals before they pair up. So this is going to make a bit more sense once we get to actually drawing these Lewis dot diagrams, or if you want to call them electron dot diagrams, that's fine too. A maximum of 8 electrons can occupy all 4 of the valence orbitals, assuming that you're talking about an element that does have 4 valence orbitals. Again, the exception is hydrogen and boron. So single electrons in an orbital are called bonding electrons, whereas paired electrons in an orbital are going to be called either lone pairs or electron pairs, but I tend to call them lone pairs. Okay, so it's very important that you know that single electrons are called bonding electrons and that paired electrons are called lone pairs. Okay. You need to know that a maximum of 8 electrons can occupy the valence orbitals unless you're talking about one of the exceptions, and the reason being is due to something called the octet rule, which is just saying that in order for an atom to be stable, you need to have, or it needs to have 8 electrons surrounding it. Okay. And you should know that most atoms are going to have 4 valence orbitals. Okay, so the parts that I've highlighted are the most important parts. So yeah, make sure that you highlight them as well. And actually, you know what? I'm also going to highlight statement number 3. Okay, those are the most important pieces coming from this. All right. So for the Lewis dot diagrams or electron dot diagrams for single atoms, we're going to follow these 3 steps. So make sure, let's highlight this box. Okay, so we're going to write the element symbol to represent the nucleus plus filled energy levels of the atom, and then we're going to use a dot to represent each valence electron. And then we're going to start by placing a single valence electron into each of the 4 orbitals, which are located to the top, right, bottom, and left of the symbol. Okay, so we're going to fill the empty orbitals first, and then once each orbital is filled up with 1 electron, that is when we're going to start pairing up the valence electrons. Okay, so when we're drawing these electrons, so let's just say this is our symbol, you can either draw them in a clockwise motion or a counterclockwise motion. Choose one of the two and stick with it. Whatever you do, do not draw your electrons top first, then bottom, then side to side. Do not do that. You will get incorrect shapes for your molecules, which is important later on. So either draw your dots that represent your electrons, either draw them clockwise, going around the symbol, or counterclockwise. Okay, so let's do some examples here. For oxygen, the group number for oxygen, if we look and find oxygen, it's in group 16. Okay, and remember that the last digit of the group number tells you how many valence electrons an element has. So because the last digit of oxygen's group number is 6, that means it has 6 valence electrons. So for the Lewis dot formula, I'm going to draw the symbol for oxygen first. Okay, and then what we're sort of imagining is that there's these orbitals on the top, right, bottom, and left of the symbol. And that's where we're going to be drawing our electrons. Now, arbitrarily, I'm going to choose to draw my electrons in a clockwise fashion, but you could draw them in a counterclockwise fashion. But let's count here. We have 1, 2, 3, 4. So now I've filled up all orbitals with 1 electron, and now I need to move on to pairing these electrons up. So we got 4, 5, 6. So for our number of valence orbitals for oxygen, there's 4. All elements have 4 orbitals, with the exception being hydrogen, it only has 1, and boron only has 3. With the number of bonding electrons, so remember, bonding electrons are the electrons that are by themselves, and they are what contribute to creating bonds. So we have 2 bonding electrons. Now for lone pairs, those are going to be the electrons that are already paired up. So that's going to be right here and right here. So there's 2 lone pairs in oxygen. For our bonding capacity, because bonding electrons help to create bonds, how many bonding electrons you have is going to tell you the bonding capacity, or how many bonds an atom can make. So because we had 2 bonding electrons, our bonding capacity is 2. So oxygen can form 2 bonds. All right. And you know what? I'm going to write down the exception that I've already said with this number of valence orbitals. So usually 4, unless you're talking about hydrogen or boron. All right, phosphorus. So let's find phosphorus. Symbol for phosphorus is P, and it is in group 15. Let's clean this up a little bit here. So, group 15, the last digit of the group number is going to be how many valence electrons you have. So it has 5 valence electrons. For our Lewis dot formula, I'm going to start off with the symbol for phosphorus, and then I'm going to start at the top and then go clockwise. So 1, 2, 3, 4, 5. So phosphorus isn't one of our exceptions, so it still has 4 valence orbitals. For the number of bonding electrons, so electrons by themselves, we have 3. For the number of lone pairs, oh, that's going to be this one right here, so there's only 1 lone pair. For our bonding capacity, well, that's correlated to how many bonding electrons you have. So since we have 3 bonding electrons, phosphorus can make 3 bonds. With neon, if I look here, neon is right here. It's part of group 18. Okay, so that means it's going to have 8 valence electrons because the last digit of the group number tells you how many valence electrons you have. For our Lewis dot formula for neon, I'm going to start at the top and go 1, 2, 3, 4, 5, 6, 7, 8. We have 4 valence orbitals. We have no electrons by themselves, so no bonding electrons, and we have 4 lone pairs. So for its bonding capacity, because there are no bonding electrons, neon doesn't like to make bonds. Last but not least, we have chlorine, which, let's clean this up a bit again. Chlorine is part of group 17. It's right there. So group 17, it has 7 valence electrons. When I'm drawing the Lewis dot formula or Lewis dot diagram or electron dot diagram, I count 1, 2, 3, 4, 5, 6, 7. Okay, so how many dots that I'm drawing comes from how many valence electrons each atom has. So number of valence orbitals, this is going to be 4 because it's not one of our exceptions. Bonding electrons, there's our bonding electron, so there's only 1 of them. And there are 3 lone pairs of electrons around chlorine. So I'm going to write 3. So this means chlorine can only make 1 bond. Now, moving on to Lewis formulas or Lewis dot diagrams for molecules, which can also be called electron dot diagrams for molecules. Essentially, we can use the same concept when we are drawing like each individual atom, and we can use that to create molecules. Okay. So, what's all in this box is very important. Okay, so step 1, we're going to draw the Lewis dot formula or Lewis dot diagram for each atom by itself, which makes up our molecule. The unpaired electrons, which we call bonding electrons, are available for sharing to form a covalent bond. The lone pairs do not do anything when it comes to bonding. The atom with the most bonding electrons is going to be your central atom. So you always place the one with the most bonding electrons in the middle of all your other atoms, and in the resulting Lewis diagram, all electrons must be paired, and each atom, except for hydrogen, must be surrounded by an octet of electrons, so 8 electrons, which is following the octet rule, and it just means that in order for an atom to become stable, it has to have a full outer valence orbital. Okay. So, for example, we have hydrogen sulfide. So, first thing I'm going to do is I'm going to just draw the individual atoms. So I know hydrogen is in group 1, so it only has 1 valence electrons. You could write the dots that represent electrons on the side or the top. Either or is fine. Okay, now for sulfur, if I look, sulfur is part of group 16 on our periodic table. So that means it has 6 valence electrons. So I'm going to just arbitrarily start on the top. 1, 2, 3, 4, 5, 6. Okay, so in order to go from just single atoms into a molecule, we need to pair up our bonding electrons because it takes 2 electrons to create a bond. So how I like to represent that is by circling the electrons that are creating the bond. So I'm creating a bond here and here. Now some people instead might represent the same molecule by just slightly adjusting the positions of the hydrogens. Okay, so I'm going to draw the sulfur again. This is an alternative way to show a molecule. Okay, and what I'm going to do is I'm going to draw the hydrogens, and I'm going to use a different color just so it's easy to see which electrons are coming from where. Okay, and I'm going to snuggle that hydrogen a little bit closer. So this either picture or either representation for me would work. Okay. Last but not least, for each of these compounds here, we're also going to be drawing the structural diagram. So essentially what that means, and it's kind of why I like doing the circles a bit better, is anytime you see a circle, that's going to get turned into a stick because it represents a bond. So how the structural diagram would work is I have sulfur, and what I'm going to do is I'm still going to represent the lone pairs where they are. But since a bond happened with this electron on the left-hand side of sulfur, I'm going to draw a stick on the left hand of sulfur, and another bond happened with like the bottom electron of sulfur. I'm going to draw a stick right there, and then there were hydrogens on either side, and there was no lone pairs on the hydrogen, so that's why I'm not going to draw them. Okay, so this would be a structural diagram of hydrogen sulfide. With methane, I'm going to do same sort of situation. Okay, so just looking ahead here, for carbon, it's in group 14, so I know it has 4 electrons, or 4 valence electrons. Okay, whereas hydrogen's just going to have 1 valence electron because it's in group 1. So because I already know what the Lewis dot diagram of carbon looks like, I'm going to kind of put it a bit more centrally, but I wouldn't expect you guys to know right off the bat like which atom's going to have the most bonding electrons. Sometimes you're just going to have to draw it out and see for yourself. Okay, so 1, 2, 3, 4. So carbon does have the most bonding electrons. That's why I'm putting it in the center. Now for the hydrogens, I'm going to place them a bit strategically. Okay, I'm just placing them around the carbon. Okay, so what you could do is you could draw circles around the electrons that are creating bonds, or alternatively, so going clockwise or counterclockwise. Okay, alternatively, you could also draw the Lewis dot diagram or electron dot diagram, whatever you want to call it, like so. And we're just trying to show, okay, these electrons, we're drawing them closer together so that it looks like they are paired up. But in my opinion, the circles communicate that these are the bonding electrons that are pairing up. All right, so now we need to go from either one of these drawings into a structural diagram. So anywhere where you have a circle around two bonding electrons, you're going to create a stick that represents a bond. Okay. So I have bonds on all sides of the carbon. So we're going to go like that. Okay, I'm just going to draw a little line here to separate the hydrogen sulfide from the methane. And draw another line here to separate methane from our next compound, which is phosphorus trifluoride. Okay, so starting out same way, we're going to have phosphorus. Phosphorus is part of group 15, so it has 5 valence electrons. So 1, 2, 3, 4, 5. And then fluoride, I'm going to place it strategically around phosphorus because fluoride is going to only have one bonding electron. So that's why I'm putting it on the outer sides. For this fluorine atom, I'm going to draw the dots counterclockwise. So 1, 2, 3, 4, 5, 6, 7. So fluorine's part of group 17, so it only has 7 valence electrons. And then I'm going to do same sort of situation here. So going counterclockwise. 1, 2, 3, 4, 5, 6, 7. And the reason why I'm doing this is so that the bonding electrons end up closest to each other. Seven. Okay. And then draw my loops. Okay, so the other way that you could represent this is by going like so. And if you don't want to use the loops, then it'd be like so. So with this, I made a slight error. Okay, so I just need to start drawing my dots on a different side. I believe I started up on the top, so let's just try this. 7. There we go. And I'm going to scooch this dot just a little bit closer to the one on phosphorus here. So let's just scooch these. Boop, and then boop. There we go. So the main goal of either of these different versions of drawing the Lewis dot diagrams or electron dot diagrams for these molecules, the goal is just to show that the bonding electrons are paired up. Okay, and where we have paired up bonding electrons, in order to go from a Lewis dot diagram to a structural diagram, you're just going to draw sticks. Okay, so phosphorus, and then I'm going to keep that lone pair on my central atom. There's my 3 bonds, and then fluorine. Okay, so I don't need to draw the lone pairs on my terminal atoms, so those are the ones that are not in the center. Okay, you don't have to draw the lone pairs on the terminal atoms, but you do have to draw the lone pairs on the central atom. So let's just write down what I've said previously. Make sure that you show the bonding electrons are paired. It's the main idea here with the Lewis dot diagrams. Okay. So as we've kind of already seen on the right hand side here, the structural diagrams, they are pretty similar to Lewis diagrams in that the element symbol represents the nucleus and all non-valence electrons. Okay. The bonds are shown with a line instead of the dots for the electrons, and lone pairs are not shown, we should say, on the terminal atoms. In structural diagrams. Show them on, and by show them I mean show the lone pairs. Maybe I should write that. And sometimes there's two central atoms. Okay, but both of these are, like if we're looking at the hydrogen bonded to the fluorine there, both of those would be terminal atoms there because they're on either end of the molecule. Or sorry, that would be a compound. There we go. So looking at this table here, I'm going to choose to do CHF3 as one of the examples just because hydrogen is a bit simplistic there. Okay, so I'll show you how to fill in this table here. So first is Lewis dot diagram of the atoms. Okay, so with hydrogen, it's in group 1, so there's only one electron. With carbon, it's in group 14, so 4 valence electrons. And then fluorine, I know there's 3 of them, but because of the limited space here, I'm going to draw just one of them because you'll get the idea. Okay, so fluorine's in group 17, so it has 7 valence electrons. So the Lewis dot diagram of the molecule, so since carbon has the most bonding electrons, that one's going to go in the center. And I'm going to strategically place the hydrogen and the 3 fluorines around the carbon. Okay, so I'm going to go hydrogen there. And then for the fluorines, since sometimes it gets a little bit confusing with like how to draw the dots so that the side with the single dot ends up closest to the carbon. What I'm going to do is I'm going to pay attention to, okay, the 3 other sides have lone pairs to them, and then the last side just has a bonding electron, so I'm just going to use this to guide my drawing. But please note, this isn't the correct way to draw like your electrons around the symbol, because remember you got to go like clockwise and just draw one dot at a time. But this is so that our drawing comes out nice fairly quickly. Okay, there we go. So you can either draw the dots kind of grouped together so that it's very clear that your bonding electrons are all paired up, or you could also draw the circles to kind of show that they are being bonded. Okay, but remember, bonding electrons do not contribute, or sorry, but please remember that lone pairs do not contribute to bonds. Okay, and then for the structural formula, wherever we have bonding electrons paired up, that's going to turn into a bond. And there we go. Next, we're going to move on to Lewis formulas or Lewis dot diagrams for molecules with multiple bonds. So for our first example here, we have carbon dioxide. So I'm going to start off the same way that I've been doing with the previous examples here. First, we start off with the atoms, or each atom of each element. Okay, so carbon is in group 14, so it has 4 valence electrons. And then oxygen is in group 16, so it has 6 valence electrons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so now we need to pair up our bonding electrons. So what we can do is we can go like this. Now, one mistake that often gets made by students is students will pair bonding electrons that are on the same atom. That's like saying an atom can form a bond with itself. That is not possible. Okay, so you always have to create connections between bonding electrons on different atoms. So that's why I'm going to pair up these. And then for the last ones, I'm going to go bond these two together and then bond those two together. So what this is going to look like is, since I have 2 pairs of bonding electrons paired up on the left hand side, that's why I'm going to draw 2 sticks or a double bond. And then same with the right side. There's 2 pairs of bonding electrons paired up, so I'm going to draw 2 sticks to represent a double bond. Now, I don't need to draw the lone pairs on the oxygens because they are terminal atoms and they are not central atoms. Moving on to nitrogen. So nitrogen is in group 15, so it's going to have 5 valence electrons. So 5, 5. Okay. And once again, we have to pair up bonding electrons that are on different atoms. So I'm going to pair up these two, and then I'll have to draw a little bit of a wonky circle for the last 2, but that's okay. So these are paired up. Okay, if you wanted to represent this diagram without drawing the circles, what you could do is you could go like this. Hang on one second. Okay, so if you're saying, okay, I would like to pair up these 2 electrons, we could move them to the center. So I'm gonna scooch this a little bit closer. Oh, let's see if it'll let me. Yeah, no, okay, that's okay. So those are those 2. Now let's pair up these 2. So those will go right here. And then let's pair up these 2. So those will go right there. So either method works. Okay, it gets a message across that bonding electrons are being paired up. Now, if we're converting this into a structural diagram, because we paired up 3 pairs of bonding electrons, that means this turns into a triple bond. So it would look like that. For some more examples here. So first one being methanol. So I'm going to start off with carbon in the center because it has the most bonding electrons. So 1, 2, 3, 4. Okay, and sometimes how the formula is written out kind of gives you a hint as to what is bonded to what. So because the hydrogens are kind of around the carbon there, it's possible that the hydrogens may be bonded to the carbon. So let's put a hydrogen here and a hydrogen there. And then for the oxygen, oxygen is in group 16, so 6 valence electrons. Okay, and this is kind of why I love the loops. It makes it a lot easier. So I can pair up these two bonding electrons, and these two. Okay, so what the structural diagram will look like is there's a single bond between each carbon and hydrogen, or the carbon and each hydrogen, I should say, and then there's a double bond between the carbon and the oxygen. Okay, there's no lone pairs on the carbon, so I don't have to draw anything on my central atom, and the rest are terminal atoms, so I don't need to draw any lone pairs on the oxygen. Okay, so typically carbon is going to be a central atom. For ethyne, we have 2 carbons, so 1, 2, 3, 4, and I'm just positioning them in the middle. And then we have 2 hydrogens, so I'm going to place them on either side. Okay, so once again, do not make the mistake of bonding electrons on the same atom. Okay, that is incorrect. So what I'd recommend is pair up the bonding electrons on the hydrogen last. Okay, so I'm going to take care of the ones on the carbons. Oop. And then we'll take care of the hydrogens. So there and there. So as a structural diagram, so I notice that there's 3 loops in between the carbons, so 1, 2, 3, and then 1 hydrogen on either side. Okay. Now, if you're wondering why I'm drawing the structural diagrams in these certain shapes, it's just because I'm trying to make sure that the terminal atoms are kind of equally dispersed around the central atom. Okay, that has something to do with Vesper theory, which we will get into later. Last but not least, oxygen. So we have oxygen 1, 2, 3, 4, 5, 6 because it's in group 16. 1, 2, 3, 4, 5, 6. And then let's pair them up. So keep in mind, you do not disturb the lone pairs when you are matching up bonding electrons. Okay? The lone pairs do nothing to contribute to bonds. It's only the bonding electrons. So then what our structural diagram will look like is that.